This is the first video in the series of videos, and this videos I will go into detail to explain what is a scalar quantity and what are the different vector quantities. And again, after this, in the next video, what we will see is we will see about the vector addition, and then I will explain about the vector subtraction. And next, then we will see the Cartesian coordinate representation, and after that what I will explain will be about the dot product, the cross product. So this is the first video, and just taking a second. So firstly, so to say that scalar quantities are something which have only magnitude, and these quantities have no direction. So when you're talking about scalar quantities, by saying that speed is an example of a scalar quantity, by saying that the speed of an aeroplane is 100 km per second, you are only giving information about the speed. You are not giving any information about the direction or the location of the aeroplane. Suppose the aeroplane is moving from A to B, so you are not saying that the aeroplane is moving from A to B with a speed of 100 km per second. By just giving information that I have an aeroplane whose speed is 100 km per second, you are giving only information about the speed, which is without any information about a direction or location of in space. When you're dealing with such quantities with only magnitude, with no direction or information about the space location, you are dealing with the quantities which is known as the scalar quantities. So taking more detailed example, you can say that there is a bowl of soup, and this bowl is filled with the soup, and this soup is located in a table, or it could be located at you can say that this XYZ plane there is. So when you're saying that you are having the temperature of the soup is equal to 100 degrees Celsius, you are just saying the temperature of the whole soup. But if I'm saying that the temperature of the soup at a point 1 to 4, I'm saying this specifically at this point the temperature is 104 degrees Celsius. So I am saying at a specific point, or even if you are saying at this point it's 100 degrees Celsius, I am talking about a vector quantity. But when I am saying that the temperature of the whole soup is 100 degrees Celsius, I am not saying at a specific point in the soup, or I am not considering any location of the soup in space. Like the soup, this might be my space and the soup might be located here, so this will be 1, 2 and 8 is point in the space. So I'm not considering any such cases. I'm just saying a simply considering the whole of my soup. So such quantities are again scalar quantities. So understanding space in very detail, so to understand the space, I am saying that this is simply my table on which I am working right now. So this will be I can represent this using the Cartesian coordinate system, which we will study, and you can simply say that this is my origin and this is my x and this is my y. So this is my minus y, this is my plus y, and this is my plus x, and this is my minus x. And so whenever I'm saying that this is my z and this is my minus z, so this is how you can represent space in 3 dimension using Cartesian coordinates or x, y, z. So if I'm having a point P here, suppose it's 1, 2 and 4, so the 1 is the x, so it is 1 here, so it is 2 here in the y direction, and you are joining these two and you are getting the xy plane, and when you are moving in the direction of the z, this point could be located at the z, which is 4. So this point is located at here, and if you are drawing the OP, which is a position vector or the vector in direction of OP, you will get the OP vector if you are drawing it from the origin. But this is how you are representing a point in space. So when you are saying that this is a OP vector, and if you are finding the magnitude of OP, so considering a simple case, if the distance of from O to P, if it's 100 kilometer, you are simply saying that the distance is equal to 100 kilometer. You are not saying where it is located in space. So this distance is a scalar quantity, but you are multiplying that 100 kilometer by a unit vector OP dash. So we will see what is unit vector in the coming lectures, but if you are multiplying that with a unit vector, so this is a OP vector and this is 100, which is the magnitude of that vector, and you are multiplying it by a unit vector. So what you are getting is that you have both magnitude and direction. You have both magnitude plus you have direction. So both with magnitude and direction, what you will get is something known as vector quantities. So that's just a basic overview understanding of what could be the scalar quantity and what could be the vector quantity. So going in more detail, so examples of scalar quantity could be something like distance, something like velocity. Without direction is known as speed. So not velocity, only speed. So something like time, something like temperature, something like volume or area. This kind of quantities could be scalar quantity because they gave no information about direction of action or location in space. So these quantities only have what is known as a magnitude. So such quantities are known as scalar quantities. Again, example of vector quantities could be something like a force, a position vector. There could be displacement. There could be velocity. It could be acceleration. So when you are dealing with both magnitude and direction, you are dealing with something known as the vector quantities. So if you are having something like a vector r, you can represent it by using the letter and an arrow which says that it's a vector quantity, and using the Cartesian coordinate system you can write it as rx ax plus ry ay plus rz az, and this is the component vectors in the direction of x and this is a component vector in direction of y, and this is a component vector. Again, your unit vector is a vector itself divided by the magnitude, and to find out the magnitude, the simpler way is to square root the magnitudes of each of the component vectors. So rx square plus ry square plus rz square. So going in more detail, what you will find is that suppose I am moving from a point, suppose this is the origin and an aeroplane is going towards the point P. So this is my OP vector and this is my OP unit vector. So my OP vector could be written as xax plus yay plus zaz. So this is how you can write that. And again, OP vector divided by the magnitude of OP will give you the OP unit vector. So going in more detail, I can simply say that my velocity of this is 100 km per second. But again, if I am saying my speed is 100 km per second, but if I am saying that my velocity is 100 km per second, and if I am saying the velocity vector VOP as a velocity vector, and if it is, I am adding the magnitude which is the speed which is 100 km, and I am adding it in a direction vector. I am using the position vector here. So I am saying that this is 100 km in the direction of OP. So to show the direction of OP, I am using the OP unit vector here. So to simply, when I am adding the position vector, I am giving more information about something like the location in space or the direction in which it is acting. So I am giving the information on the direction by using the unit vector in that direction. So the unit vector in the direction OP is this, which can be found out from here. So this velocity has more information, the vector of the velocity has information about the direction in which the velocity is acting. So the aeroplane is moving from the point O to P, and the velocity is 100 km in this direction. So when I am dealing with such quantities, I am dealing with something known as the scalar quantity. So again, having more information, again adding more information. So some examples of scalar quantity, as I said, could be like my velocity, my force, etc. So if I'm having two objects like A object here and B object, if I'm saying that this is charge Q1, this is a charge Q2, again if you know the Coulomb's law, then you can say that this is my position vector R1, this is my position vector R2, which is showing the distance. And again, if I'm having a force like FBA, that is a force on B due to A, so this is both plus charges, or this is both having positive charges. So when the force on B will be due to A, it will be in this direction and it will be a repulsive force. And when I want to represent that force by using the Coulomb's law, that I can say that FAB is equal to Q1 Q2 divided by R square. Here the R square will be RAB square, or this is RA, this is RB to be more specific. So this is my RAB unit vector, RAB vector, and it will be divided in the direction of A to B. So it will be given by the direction of unit vector A to B. So that's how you are giving a vector force, and you are having this unit vector RAB, which will give the direction in which the force is acting. So that's how we have defined or seen what scalar quantity was in more practical way. We saw how to represent the vector, and again we also saw what were the vector quantities and how it's possible to represent the vector quantities. So that's all, and